Good afternoon, everyone. I am Laura Rossi. I'm a PhD student at the Karlsruhe Institute of Technology in Germany, and today I'm going to present my research topic about fiber-reinforced alkali-activated materials. In this presentation, I will briefly introduce my research topic. I will talk about the experimental program and the results obtained so far, and I will conclude talking about some future perspectives. Supplementary cementitious materials have been widely used as cement replacement in traditional concrete to improve both mechanical and durability performance, and also to reduce the environmental impact related to cement production. However, if combined with an alkaline solution, these aluminosilicate-rich binders can react, forming a new construction material with similar performance compared to OPC concrete. Depending on the chemical composition of these binders and mainly on the calcium content, two different groups can be defined. High calcium silicon-rich binders, which react with alkaline solution, leading to the formation of a cash gel, and the low calcium alumino-rich binders, such as fly ash or metakaolin, which reacting with an alkaline solution lead to the formation of a Nash gel. In this work, only the first group of binder is investigated. Talking about fiber-reinforced concrete, this type of composite has found in the last decades a wide utilization in both structural and non-structural application in the construction field. So why should we use alkali-activated materials instead of traditional concrete? Previous researches demonstrated that alkali-activated material can be a suitable alternative to traditional concrete, not only from an environmental point of view, but also from a mechanical point of view, as they show similar or even better performance compared to traditional concrete. In addition, this type of materials can show better durability performance, such as a better resistance to chemical attack, chloride ingress, and fire resistance. For this reason, the addition of fiber into the alkaline matrix can improve the durability performance because the fiber can mitigate crack propagation and also increase the load-bearing capacity even in a cracked state. In hardened plain concrete, microcracks exist and pre-exist even before any stress is applied, mainly due to shrinkage and thermal deformation. When a tension is applied, the microcracks start growing at the weakest link of the composite, which is the aggregate matrix interface. The microcrack starts growing and they propagate in an unstable manner until crack localization. In plain concrete, only aggregates can breach the crack. However, in fiber-reinforced concrete, the bridging capacity of the aggregates is widely improved by the incorporation of fibers, which can bridge and branch the crack, improving the fracture energy and the toughness of the material. However, the performances of a fiber-reinforced concrete are affected by different parameters. First of all, the fiber material. Both organic and inorganic fiber can be used as reinforcement into traditional concrete. For example, steel fibers can be used to improve the mechanical properties and in particular the flexural post-cracking behavior, while, for example, microsynthetic fibers can reduce shrinkage deformation. However, in addition to fiber material, also fiber shape and geometry, distribution and orientation, and especially the number of fiber crossing a crack can affect the performance of the fibers and the final properties of the composite. An important role is also played by the fiber matrix interaction and especially by the interfacial transition zone between the fiber and the matrix, because this is affecting the short-term and long-term mechanical performances of the composite. This research work were defined following three different phases. A first planning phase in which binder, mix design, fiber type, and volume fraction were defined. A casting phase in which all the samples were prepared, and a testing phase in which the samples were tested according to European standard. Cubes were tested to evaluate the compressive strength development during time, and 3-point bending tests were performed to evaluate the flexural post-cracking behavior of the composite. In the planning phase after different trial, a good workable mix with a good setting time and a compressive strength higher than 30 MPa after 28 days were developed using blast furnace slag as binder, sodium hydroxide and sodium silicate in combination with water as activators, and 3 different Dramix steel fiber were used for this investigation. During the casting phase, all the 10 mixes were prepared following the same mixing procedure and applying the same curing condition. A total of 120 cubes and 80 beams were cast. 3 cubes after 1, 7, 14, and 28 days were tested to evaluate the compressive strength development during time, and 3-point bending tests were performed on 6 beams for each mix, following the recommendation of the FIBRE Model Code 2010 and the European Standard EN 14651. 3-point bending tests were performed on notched beam, and every mix were classified following the recommendation of the FIBRE Model Code 2010. The results of the compressive strength are shown in this diagram. As you can see, the compressive strength increase from 1 to 28 days for each mix. And also the compressive strength after 28 days show a similar trend for all the mixes investigated. In fact, the compressive strength increases with the increase of the fiber percentage from 0.25 to 0.50, but the compressive strength decreases with an additional increase of fiber content from 0.50 to 0.75% volume fraction. The compressive strength drop you can see on the left of the graph is corresponding to the mix with 20 kg per cubic meter of Dramix 3T fibers, and this is due to a different water binder ratio. For this mix, in fact, a water binder ratio of 0.51 was used instead of 0.48 as for all the other mixes. The different water binder ratio is related to the utilization of wet aggregates, and it can also help demonstrating that also for alkali activated material, the water binder ratio plays an important role in the compressive strength development. In fact, a higher water binder ratio corresponds to a lower compressive strength. However, as for traditional concrete, the addition of fiber do not really affect the compressive strength. As we can see, the compressive strength value of fiber reinforced concrete compared to the plain concrete, the first on the left, it's not so different. In this slide, the load CMOD crack mouth opening displacement diagrams obtained directly from the 3-point bending test are shown for each fiber type. As we can see, for all the fiber types, an increase of fiber content corresponds to an increase of the residual flexural behavior. However, if the fracture energy is almost double with an increase of fiber content from 0.25 to 0.50, increasing the fiber content from 0.50 to 0.75 do not lead to a similar increment of fracture energy. In the table under each diagram, is it possible to see the classification of each mix following the recommendation of the FIBRE Model Code 2010? Every mix is classified with a number which represent the characteristic residual flexural strength corresponding to a CMOD of 0.5 millimeter, and a letter which represent the ratio between the characteristic residual flexural strength at a CMOD of 2.5 millimeter and at 0.5 millimeter. In this slide, instead, we can see the load CMOD diagram for every fiber percentage. And as we can see on the left, with the lowest fiber content, so 0.25% volume fraction, the best behavior is obtained with the Dramix 4D fibers, while 3D and 5D perform very similar, even if they have different performances and properties, especially the tensile strength of Dramix 5D is almost the double of the one of the 3D. This behavior could be due to the compressive strength of the matrix, which is not high enough to allow the 5D fibers to perform at their best. With an increase of the fiber content from 0.25 to 0.50 or even to 0.75, the performances of the fibers are quite similar, even if the 3D fibers are the one with the lowest post-cracking residual flexural strength. And 4D and 5D almost perform in the same way. And this is also due to the same explanation given before. From the experimental results of this investigation, it was possible to evaluate the behavior of fiber into an alkali activated matrix, and it's possible to say that the addition of fiber affects positively the post-cracking behavior of the composite, and that different fibers with different geometry behave in a different way. However, additional investigation and experiments are needed. In particular, direct and indirect tensile strength tests need to be performed to fully understand and characterize the material and to define correlations between the mechanical properties as for traditional OPC concrete. For this reason, OPC-based mixes with the same fiber types and fiber percentage as the alkali activated matrix need to be cast and tested to evaluate if the same fiber with the same percentage and volume fraction can behave in the same way in different matrices, both traditional concrete and alkali activated concrete. In addition, casting and testing OPC-based mixes will help to understand correlation between the mechanical properties and also to evaluate if existing models and the question for traditional concrete and traditional fiber reinforced concrete can be applied for alkali activated materials. The main goal of this research, in fact, is to evaluate and understand if these existing models can be applied to alkali activated concrete, and if needed, how they can be improved in order to apply this new alternative material in the construction field in both structural and non-structural applications. Thank you for your attention. I will be happy to answer to all your questions.